The discussion on decision trees. We'll be looking at 4 different cases of decision trees, and that's the exact question that we've been asked in the assignment also. The first case is on discrete input, discrete output. But before that, let's remember why we were talking about decision trees. In the introductory lecture, we were talking about things like Uber and Tesla car crashes. Imagine if you are the engineer or you are the researcher working behind these things. Sometimes you're working with very complex models such as neural networks, some of which are not very useful for interpretability in the direct sense. You'll have to do something out of the standard to make them interpretable. This is where models like decision trees are very, very useful because they're fairly interpretable. We'll be looking at this example for the purposes of the first part of the lecture for decision trees. As you can see that the output variable is what type? It's a discrete type, so what kind of a problem is this? It's a classification problem, and what are the features? Are they discrete, are they real? The features are also discrete. We will not be looking at the day as a feature for now. Imagine that if you were to learn a complicated neural network like this, now each of these arrows or each of these connections, think of it as it's representing some number. So if you have to tell the relationship between whether or not I will play tennis, with respect to the input attributes, the relationship might be a bunch of these complicated numbers. Can you make sense of those easily? Probably not. Now imagine if you're given a tree-like structure, something like the following. Now can you make sense of the relationship between input and output? What does this tree tell us? It says that when the outlook is overcast, I always play. Makes sense. Some people like to play when it is overcast. When it is sunny, then you have to check for the humidity. If the humidity is high, you don't want to play because it is going to be both hot and humid. But if it is sunny and the humidity is normal, you can still play. So this seems to be a fairly simple interpretable model that we can learn. Decision trees are also used for a variety of applications, including medical diagnosis. In the last lecture, we discussed that imagine if you were to go to a doctor, and a doctor is again given a neural network or a very complicated machine learning model which is very happy with it. They will probably not like it. But if they're given something like the following, they will probably embrace such technology. This is talking about things like the number of vessels, whether this is exercise induced angina or not. And then you can figure out, and you can narrow down, figure out the exact symptoms and the exact disease. A lot of the algorithms that we're discussing today are given by this researcher who passed in 2005 called Brieman from Berkeley. And if you notice, he gave us the random forest, classification and regression trees, bagging, boosting. So one of the foremost researchers in the area of work that we discussed. We also last time looked at the fact that learning an optimal decision tree is non-trivial. So for example, if we look at this particular tree, how do we know that this is the optimal tree? Could we have some other attributes at the top? Could we have some other attributes? So we have an exponentially growing tree. It's non-trivial to figure out what is the optimal tree. And optimality could be defined in terms of the accuracy that we're trying to get. We discussed the core idea that because the algorithm is non-trivial, could we look at a greedy algorithm? Greedy means you don't look too far into the future, you just look at one step into the future. And the core idea is to choose an attribute as a split point or as the node for which you make a decision, which gives you the best estimated performance gain, where the word estimated and performance gain are going to be very important in this context. We also looked at the fact that greedy is not going to be optimal. In this case, if you are in the yellow car and you want to you take a greedy decision that you want to reach a destination very quickly, you might take a left. But that is a really bad decision because then you'll get caught up behind these trucks which are moving slowly. If instead you just kept on moving in this same path, following the cars, you'll reach your destination early. Okay, so now let's try to understand what do we mean by various estimated performance gain. If you notice that we have 14 examples, and if you look at only the output attribute of concern, we have out of these 9 yeses and 5 no's, right? Imagine if in the play field, in the play attribute, we have 14 yes or 14 no. Is it a simple or is it a simpler classification problem then? Why or why not? You can. Sorry. Why do you need a one level? Like, do you even need a tree if the prediction is always yes or always no? It's a trivial decision, right? You then always say that I will always play tennis or I will never play tennis, right? So what we're saying is that 9 yes and 5 no is a harder decision tree to classify, or is a harder problem to classify compared to 14 yes or 14 no. So this is going to be one key intuition.
Please come to the electrical lab.
We have 14 yes or 14 no. That would be trivial to solve. So the key insight is that the problem is easier when there is lesser disagreement, right? Can we now quantify the notion of disagreement? I think from next time onwards, we'll set the ground rules very clearly. If you're entering 5 minutes late, please do not enter. Or please enter from the beginning. Right? So we're talking about the problem is easier when there is lesser disagreement. Here we said that 9 yes and 5 no have some element of disagreement because it's not a trivial decision. Whereas 14 yes or 14 no, there is no disagreement. You'll always predict them to be either playing or not playing. So the next question to all of you is, what statistical measure would you use to somehow quantify this disagreement? Entropy, if you have studied this, and okay, we studied this in the last lecture also. Could you think of any other statistical measure? So another question: when is it even more hard? So 9 years and 5 years. When would it be even harder to do the classification? 7 years, 7 no's. Because then you're almost randomly telling the split is very. We end up using a statistical measure known as entropy. Now, entropy has been studied in various contexts, including thermodynamics and information theory. We are going to be looking at the information theory perspective here, where it's a statistical measure to measure or characterize the impurity or purity of example. It's given by this formula of minus p log p, where you're summing over the probabilities of the different events or of the different samples that you can get. Imagine that you have only 2 possibilities, only 2 sets of outcomes, either plus or minus. So then can we say that p of plus plus p of minus is equal to 1? You have only 2 possibilities. So entropy is now plotting this. It's basically plotting minus p plus log p plus and minus log of p minus times log of p minus, right? And the entropy is going to be maximum when p plus equal to p minus equal to 0.5. So what this plot is showing you is that when the probability of plus is 0, it means that the example or the outcome is going to be negative. right? So there is no disorder, there is no disagreement. Likewise, if we go to the other extreme, if probability of plus is 1, it means that the probability of negative is 0, which means that there is no disagreement. The maximum disagreement again happens only when probability of plus is equal to probability of minus, right? And in the information theory context, entropy is also used to, in some sense, in the intuitive sense, you can understand it as the average number of bits you have to transmit in order to pass the signal. So again, if it was only plus, you don't need to send any information because it's only plus. If it's only minus, again, you don't need to send any information. Only when it is either plus or a negative, there is some confusion and you need to send in the actual signal. Sorry. So P of xi, like xi, if you go back to the previous example, xi would be no or a yes. And in this particular example, it could be plus or minus. Okay, so now we've looked at some notion or some statistical measure of telling the disagreement, which is the entropy. But if you remember, we were saying that we want to build a greedy algorithm which gives us the biggest estimated performance gain. Right? So can you now think of something which is related to entropy, but is also talking about the performance gain? You get the question. We have entropy for a given set, and then we're talking about biggest estimated performance gain. Right? So you have to somehow link entropy examples and you have to choose an attribute. So connect all of these dots and come up with
the attribute which gives us least entropy. Like suppose if we use humidity, if it's high, the question is high and normal. So
Okay.
high most are yes and normal most are no, something like that. So we have to find out attribute.
okay, so what Adhibab is saying is pretty much on the line, pretty much on the track. He's saying that we have to pick an attribute which leads to a reduction in entropy. So I'll put it this way. Because at the end of the whole thing, you want a scheme which is easy to classify. For example, we said 14 yes and 14 no is very simple. What we're trying to do is to pick up attributes which simplify the process. Right? So the first question is, can we use outlook as a root node? Just look at all the rows where the outlook is overcast. Do you observe something? What do you observe? For outlook equal to overcast, you always split. What is the entropy when outlook equal to overcast? 0. There is no disorder, there is no disagreement. So it seems like outlook could be potentially a good choice, but we'll have to still look at all the other possible attributes and see their relative entropies also. So thus we come up with another formulation, another statistic, which is known as information gain, which is said to be the performance gain or the reduction in entropy when you partition a set of examples S on an attribute A. You have a set of 14 examples where the set is known as S, and what are the attributes you could pick? What are the attributes you could pick to split? You could pick outlook, temperature, humidity, or humidity, right? So A is a set of these 4 attributes: outlook, temperature, humidity, and humidity, and S is a set of these 14 examples. Right? And now what you're trying to say is that the gain, in the information gain on these set of examples S, when you're splitting on an attribute A, is given by the entropy of S. So when you're trying to calculate the gain, you first need to calculate the entropy before you split and after you split, right? So the entropy before you split and after you split is for each of the examples. For example, outlook equal to overcast, outlook equal to sunny, and outlook equal to rain. You'll have 3 different subsets. You can calculate the entropy of each of these, but each of them have a different number of examples, right? So we somehow need to weigh them accordingly in the proportion of the number of examples. So thus this turns out to be entropy of S minus summation the number of elements in the specific subset once you've chosen a value divided by the total number of examples in S times the entropy of SV, and you sum it over all the possible examples or all the possible values which an attribute could have taken. Is this clear? The formulation clear? This should have been ID3. So now I'm going to quickly walk over the entire algorithm for use for creating the tree, and then we'll go one step at a time. Right? So don't worry if you don't get it in the first node. We have to create a root node for the tree. In the previous case, we saw it was output. If all the examples are plus or negative, is there any classification we need to do? So you can either predict that to be plus or negative based on if all the examples are plus or minus, right? But that is not going to be the case very likely, at least in the beginning. If the attributes is empty, then you have to choose the most common value of target attribute in examples. So the examples is the set S of all the samples that we have. Target attribute is the attribute of which we're trying to correctly identify, which is whether you play or not. And attributes is the set of 4 attributes which we are trying to use and to construct the tree. What do you think means by if attributes equal to empty? When will that kind of a scenario occur? Okay, once. So attributes equal to empty when you have exhausted all the possible attributes in creation of the tree. There is no possible attribute left on which you can split again, right? And then we begin a loop-like procedure. We first pick up an attribute A from all the set of possible attributes which currently are available to us in a way that it has to best classify the examples. So now we've already looked at the notion of best classification. What is the notion of best classification? Which gives us the highest information here. Then you set A to be the root of the tree, and then you have different values B of the particular attribute, right? And for each value, we create a branch. Now this will give us different subsets of the data. And once we have that, we can then recursively call the same procedure on the subsets of the data that we get. We call ID3 and examples of which are taking the subset value like outlook equal to sunny and the target attributes, and you subtract the attribute which you have used thus far, because it doesn't make sense to split on it again, because examples underscore V would be all the examples where, let's say, outlook equal to sunny. So you cannot split it again on outlook. Let's go over this algorithm one step at a time. First, you set up with an empty root node. Right? Then what was the next step? If all the examples are plus or minus, then you just set the leaf node to be plus or minus. But that is not the case for us. We have the training data which looks like the following. First, we calculate the entropy of the set S. Right? We have 9 yeses and 5 no's. So entropy can be calculated as minus the probability of no. Probability of no is 5 by 14. Probability of yes is 9 by 14. So minus p probability of no times log base 2 probability of no. And we use log base 2. Any idea why? Because of the connotation, because of the relationship between the bits and the information channels. So this turns out to be minus 5 over 14 log base to 5 over 14 minus 9 by 14 log base to 9 over 14, which is 0.94. What is the maximum possible entropy we can get for a set? 1. This is very close to 1, which is telling us, which is indicating that there is a high amount of entropy. Right? Now let's look at different possible attributes for splitting. Right? So if we go back to the algorithm, we said that you pick up an attribute A from the examples, from the attributes which best classifies the example. So imagine this will be a for loop where you have to cycle through all of the possible attributes and find the information gain for them. Right? So let's say we start with the attribute A equal to outlook. And now we omit all the other columns because they are not of relevance to us. Outlook, 14 examples, outlook is sunny, overcast, or rainy, and play is within no rains. Can you think for a minute and calculate the entropy of this set? Once you split the information gain, once you split on output, can you calculate that? Entropy of the set S is 0.94. You have to split on outlook attribute and tell me the information. And you can give a rough estimate. You don't need to be. I don't think all of you are trying to calculate. Okay, I'll walk over the solution now. The way you want to go ahead is you first split the example, the 14 examples into the 3 subsets. Right? First, you have outlook equal to sunny. You have 5 examples in which you have 3 times you don't play and 2 times you play. The entropy of this particular set is minus 2 over 5 log base to minus 2 over 5 and minus 3 over 5 log base to should have been 3 over 5, not 3 over 5. Correct that. And this turns out to be 0.971.
Let me do the correction right away. On the right hand side, you basically the formula. So minus, once you have outlook equal to overcast, you have 4 yes, 0 no, the entropy is going to be 0, there is no disorder. And when you have outlook equal to rain, you have 3 yes and 2 no, the entropy is the same, minus 0.971. One lesson, one very quick lesson here is it doesn't really depend on how many yes and no you have, as long as the relative distribution is the same. So the relative proportions are the same, the entropy will be the same. And then we can calculate the information gain via this formula. We can take 3 different values, rain, sunny and windy, and use this this quantity S B over S, the cardinality of this is telling us the proportion of examples in each of these subsets. And then the calculations turns out to be the entropy of S minus 5 over 14 because there were 5 examples when the outlook was sunny, 5 examples when the outlook was rainy, and 4 examples when the outlook was overcast. This calculation turns out to be 0.246. We have to repeat the same calculation for the other attributes. And I've done that already for you. Turns out that the maximum information gain that you get at this possible junction is using the attribute outlook. And the information gain is 0.25. For humidity, it's less. And for wind and temperature, it's very low. The information gain is very low. You could very quickly see that and confirm that from the examples also. So if you look at temperature, is it giving you a lot of information? Let's say you consider the case for temperature equal to hot. You have, for the first 2 examples you do not play, for the third example you play, and for the fourth example you play. Right? So the entropy of this set is going to be 1, because the probability of playing and not playing is equal. When the temperature is mild, you once play, you do not play the next time, you play, you don't play. So again, the entropy is going to be fairly high because the proportion of play and don't play is fairly similar. And once the temperature is cool, you play once, you don't play, you play once, you play once. While the entropy of temperature equal to cool is relatively low compared to the other 2 subsets, but still overall the entropy turns out to be relatively large. Okay, so now we have identified that outlook is the attribute that you choose, and then you put 3 different branches because outlook can take 3 different values. So at this stage, the tree will look something like the following. Why have I labeled yes for outlook equal to overcast? Because all of the examples for outlook equal to overcast are yes. Let's go back and confirm the algorithm. If all the examples are plus or negative, return root with label equal to plus or negative. Right? So the idea was we once get a root, then for each value you add a new branch, and then you recursively call identity, the same algorithm again. And when the algorithm is invoked again for this question mark, it picks up the answer as yes because all of the answers, all of the labels in this particular example are in this particular subset are yes. But we still have 2 question marks for outlook equal to sunny branch and outlook equal to rainy branch. What happens now? So what is the set that we use here now? We use the set S here with outlook equal to sunny attributes. Right? This is a smaller set compared to the original set that we started with. And what is the set of attributes left? All the attributes except for outlook. We recursively call the same procedure now, and the data set will look something like the following now. When outlook equal to sunny, then you have temperature, humidity, windy, and play is either no or yes. Now looking at the table without doing any calculation, can you tell me which attribute will be picked up next? Why would humidity be picked up? Because once humidity is, if the humidity is high, you don't play. If the humidity is normal, you play. Right? It's a simple decision now with no amount of with absolutely 0 disagreement in the labels. You can of course do all the calculations and still put the same result. And what do you think is the information gain so what is the information gain on using humidity? It's the same as the entropy of the set. Right? Because you're able to gain all of the possible information you could have gained if you split on this attribute. So then, for outlook equal to sunny, you choose humidity as the next node, which has 2 values, high or normal, and for both of these, you're able to perfectly classify into no or yes. What happens for this question mark on the right hand side? We repeat the same procedure. We now choose a subset of examples where outlook equal to rain. This looks something like the following. Now, if you carefully notice, whenever the wind is weak,
you always play, and whenever the wind is strong, you don't play. Again, it might make sense intuitively also if you don't want to be playing when the wind is very strong. So again, the attribute windy will give you the highest possible information gain in this case, and thus you end up creating this particular tree, and the procedure will stop now. You don't have anything else to do. You don't have any other question mark left to now. Right? Any questions till now? Okay. How do we predict? So thus far we have created a tree which is akin to learning or training. How do we do prediction for an unseen sample? Because that's the broad task we want to do. So the idea is that you just walk down the tree, or you just iterate over the tree. For example, if the question is you have high humidity, strong wind, sunny outlook, hot temperature, what is the prediction for this example? How many say no? Anyone say yes? So fairly trivial, right? You look at all the attributes. You look at the attribute which is at the root, which is outlook. You have sunny outlook. You walk down this branch, outlook equal to sunny. You have high humidity. You walk down, outlook equal to sunny and humidity equal to high, and the prediction is. Interestingly, the other observations also weren't even useful in this case. Okay, question for all of you. For some reason, let's say we are constrained by memory or some processing power or there is some particular reason. You've been told that you can create only a depth one tree. You cannot go deeper into and create all the possible levels in the tree. Only depth one for the current data set. How do you think will you create that?
So we will take the possibility of outlook. I mean, in one case we are sure. In other case we will take the maximum outlook.
Excellent. So the answer which they are giving and which is correct is you apply the same set of rules which you have been doing for ID3, but you will not dive deeper into the tree. Once you have chosen an attribute to split, you just then choose the most common occurring value for that particular path, right? Because you don't have an option. You cannot go deeper into the tree and split up further attributes. Okay, so even before that, what is the depth 0 tree for this example? There is no attributes. Is it a yes or is it a no? It's a yes because there were 9 yes and 5 no's. And what is a depth 1 tree? So outlook still remains the most important attribute. If outlook equal to overcast, you already know that you are going to be a yes. And then you classify based on the majority of examples. So for outlook equal to sunny, for most of the examples you don't play. For outlook equal to wind, for most of the examples you play. Also the most is slightly ambiguous because it's only 3:2 ratio. I think it's 3:2. Now let's come to the second part of decision trees where the input is discrete but the output is real. Could you think of any example where the discrete, we have discrete input and real output? I just want some particular application. Stock market, what are the input variables?
Politics and other things.
Okay, so you want discrete input, real output. Could you just modify the previous example to make the output variable real instead of the discrete? Probability of playing, okay, you could do that. What about the number of hours you play in a week? You could do something like that, or number of minutes you play. So that is the example that I have over there. Everything else in the table remains the same. I have randomly put some numbers for the minutes played. So they may or may not make sense in many of the cases, but this is just for illustration. The next question for all of you is, previously when the output was discrete in nature, we used entropy as a measure of impurity. What is the measure of impurity for cases of regression, or when the output variable is real in nature? Error? Mean squared error, okay. Any other? Deviation from? Deviation from mean, yes. So do these answers make sense to you? Again, what we want is ideally that for one particular branch of a tree, you have very little disagreement. In the discrete case, you wanted all of them to have the same labels. In the real output case, you want all of them to be fairly similar in the sense that they don't have a lot of deviation among them. So deviation above the mean is a sign of disagreement. You could use things like standard deviation or variance, right, to tell something about the impurity of a particular thing. The variance for this particular set of examples that we saw is 335.3. Okay, what is the information gain analog now? We've got an analog for entropy, which is, that's a variance. What's the analog for information gain for the real output?
This variance of standard deviation.
Reduction in variance, not less variance. How much variance are you able to reduce once you do a split, right? And this again has to be weighted by the number of samples. Although there is a strict disclaimer at this point, there are at least 3 to 4 different variations or different impurity measures that are used for regression. And some of the algorithms, some of the implementations that you study online, some of them don't consider the weighted case, some of them consider the weighted case, some of them look at standard deviation, some of them look at variance, some of them mean squared error, etc. Some of them mean absolute error. So there is not a single consistent one measure which I could give to you, but the key principles will remain the same. And as you see in a minute, there are some amount of weird things which happen in the real case which do not happen in the discrete case. So let's apply the same technique now. Let's try to see if we can split on the wind attribute. Right? Originally for this particular data set, 14 examples, the variance was 335. As we had done previously, we split on wind equal to weak and wind equal to strong. You get 2 different subsets. You calculate the weighted variance for this particular subset for wind equal to weak, which turns out to be 8 over 14, which is the weight or the proportion, times the variance of this set, which I've calculated to be 317. So this number computes to 181. And similarly, for the case when wind equal to strong, you compute the weighted variance as 6 over 14, 6 examples out of the 14 examples, whose variance is 261, and this turns out to be 112. And we can then calculate the information gain for the different cases. Now, this slide tells you what I was talking about, that there is something weird which is happening in the case for continuous output. Previously, we were talking about information gain as always being a strictly non-negative multiplier. But in this case, we can see that sometimes information gain can be negative also. So again, I'm not really sure about some theoretical backing of this or one particular best metric of information gain to be chosen here, which will always be a strictly non-negative margin. So that's up to you to figure out if you can. But what's clear from this example is that the attribute bend is the most useful attribute to split upon at this stage. Right? So we go ahead, we do the same thing as we've done previously. You put wind as the first node, wind equal to weak and wind equal to strong as 2 branches. For wind equal to weak branch, we then give some select examples. Let's assume that we now figured out that outlook becomes the most important attribute to split on based on the information gain criteria that we've set up. And then you'll again have 3 branches of sunny, overcast, and rain. And let's imagine that for the overcast case now, where the wind is weak and the outlook is overcast, you have, let's say, only 2 examples, where the minutes where there's 40 and 35. And let's imagine that you cannot go any further. You cannot split further into the tree, or you're not allowed to go beyond depth 2 trees. So then what is the output that you predict for a forecast? In the previous case, you predicted the mode, or the most commonly occurring value. In this case, you will predict some kind of a metric which summarizes. It could be median or mean. Let's for now take mean as the output. So thus the tree might do something like that. Right? Any questions to now? Yeah, so you pick the win attribute because it gives you the largest reduction in variance. And then you split it across the different values of strong or weak, which will give you different subsets. On each of these subsets, now you will perform the same procedure ID3, but you not consider the win attribute. And then let's assume that outlook turns out to be the most important attribute. Again, outlook has three branches, sunny, overcast, or rain. And then again, for outlook equal to overcast, you get some example issues. Now you say that you're not allowed to go beyond 2 levels. And then you predict the output to be the mean of all the examples that exist. Any other questions? Okay, so now let's look at the third type, where the input is real, but the output is discrete. Okay, tell me some examples now.
Same example, range between the centimeters and temperature between Kelvin.
Sorry.
Same example. Temperature between Kelvin, range between the centimeters and
The output will.
it will be a
Okay, so what they're suggesting is that the input is real, as in the range would be in amount of centimeters or millimeters, temperature could be in Celsius or Kelvin, and the outlook could be in terms of some other physically measurable real quantity, and the output could be whether you play or not. That's one example. The other example is from the assignment, the iris data set that you've been given. So that is telling you about different species of flowers. You're looking at certain attributes of them, which are numerical attributes, and the output is a class. Whether it's one of the different classes. So it's useful to think in that. So let's consider a data set. For now, let's look at only one simple attribute, temperature, and play tennis is yes or no. The question here is, how do you find splits? In the previous case, it was easier to find splits because the attribute could have taken different values. But the attribute here is on a real number line. How do you find the splitting criteria?
Greater than the average, less than the average.
Greater than the average will not work. But that's a good start. So the idea here is that you first sort the attribute in an increasing or decreasing order. And then you accordingly also change the attribute. So sort the entire table by the attribute in increasing or decreasing order. And then you try to find the splits and the points where there's a change in the output. So from 48 to 60, the plate and its attribute is changing. So think of it as there is something happening between these two numbers on the real number line, where the decision might vary. So you then find splits as 48 plus 60 over 2. So greater than 48 plus 60 over 2 and less than 48 plus 60 over 2. This gives you a subset consisting of D1, D2 and D3, D4, D5, D6. Right? That's the first split. Let's imagine you have only one attribute and you have to do multiple splits on this. You could then also choose another splitting criteria as 80 plus 90 over 2. Right? That would then partition this data set into D1 to D5 and D6. So one thing which you might have noticed thus far in this series is it's really partitioning algorithm. You have a space in, let's say, 3 dimensions, and you're just trying to split that or partition that based on some attribute. Right?
But like there should be there should be a limit for number of edges of partition. Like I can partition 5 different blocks, one each, no, yes. That would be nice.
So the question, I'm just repeating for the purpose of the recording. The question is that splitting a lot number of times is not very ideal. If you keep on splitting one attribute across multiple split points, that's not very good. So what could you do about that? So if anything is bad, then you limit that. So if you know that going beyond a certain depth is bad, or partitioning the space across multiple split points is bad, then you limit that. To illustrate that point, let's look at one example now. And if that's not clear, you can discuss it. You have two attributes, x1 and x2, and you have three different classes, blue, green, and red, right? So now you want to partition this two-dimensional space x1 and x2 so that you can accurately classify these three classes. Can anyone tell me one good starting point of splitting? So you have to split this space, which means you have to somehow choose some split points for x1 and x2. Anything, so you don't need to be accurate. x1 at -1 or x1 at -1. Let's see what is the answer that I have. The first split, according to the algorithm that I have, was at x2 close to 2. Right? So this has now partitioned. So one split has partitioned the space into two separate pieces now. And now if you can see, it's going to be very good at classifying. So this is in some sense telling you green and blue very accurately, but it's not good at classifying red as of now. Okay, what do we do then? Let's again split. So previously we split it on x2 or y. Let's now split on the other attribute. So one practical way in which people implement decision trees for such cases is they alternate between the attributes, or they look at all the possible attributes and figure out which is the best. We now split it again into another attribute based on x1. x1 is greater than or less than a particular value. Now we have three different regions. Let's now try to do what Anupam was saying. If you keep on doing splits, what happens? What do you think will happen if I create another split now? So you look at some examples of red which are over here. You look at some blue examples which are getting into the red region. You look at some green examples which are getting into the red region. More or less you're able to capture the pattern. But then there are some outliers, some deviating points. Let's now increase depth to 3. So surprisingly, nothing much has changed beyond the fact that there is another area being added over here. Now things will get interesting. So depth equal to 4. Now can you see the new split that has come across? Now you're also able to accurately predict these red examples because now you've chosen another split and you're able to, this particular region which was previously blue is now being demarcated as red. If you further increase the depth, now you're able to also accurately classify these set of green examples and these set of green examples. You can keep on going, and so this particular split which you see now was done specifically only for this one example. One green example and one blue example. Increase it further, and now it looks like a very complicated thing. So you will not want to do this. Why exactly? We'll come to that in the second part of the lecture in a few minutes. I think it's a good point. We'll now break for 10 minutes, come back and meet again for 45 minutes to 1 hour. Is that fine?